day 5 of this event, the IVC Geophysics for Engineering and Environment, from theory to practical applications. You remind me that I am Indra Gunawan from Geophysical Engineering. I am the chairman of this session. And at this evening, at this session, joining us is an expert from ITB, Dr. Alven Rudiawan. And he is a lecturer from Geology, Institute of Technology Bandung. He is an assistant professor at Geodynamics and Sedimentology. He has finished the bachelor degree in ITB at 2006, and then he got the master degree from University of London at 2010, and also got the master degree from ITB at 2011. And then he got the doctoral degree from University of London at 2016. Tonight, Dr. Alven will talk about the fracture identification and characterization. Let's welcome Dr. Alven Rudiawan. Today, it's so good to have you here, Dr. Alven, and thank you so much for joining us. And okay, and now let's start our class. Dr. Alven, you have about 50 minutes to your lecture, and then following by 20 minutes to the discussion. Please.
All right, thank you very much. Just to be clear, the talks are in English?
Yeah, in English, please.
Okay, pardon me that I would like to share my screen. It's still disabled for participant to screen share.
Okay. I'm sorry.
Mas Indra.
Okay. You might start.
Right. So, good evening, everyone. Again, apologies for a slight delay. I was in campus since the morning. I wasn't expecting the lights gone off. It was off at the couple of minutes ago, and then the internet went down. So I'm using my phone at the moment. So I'm sorry if there will be a little bit of stuttering during the presentations, waiting until the hotspot's coming back. The light's on, thankfully, so you can see my face. Just maybe good, maybe not good for all of you. Some of you may already know me from the class. Perhaps we've seen each other in the class. So I would like to give you a bit of overview about what it is related to fault identifications and how we mapped it on the subsurface or on the surface using some helps from the geophysical tools. Not really going to be very thorough in that sense. I mean, I will give you some examples about the data that we've been used throughout the years until today, perhaps, in giving you some sort of a census about how the geologists think and how you are as a geophysicist or fellow geologists here can share the knowledge and also share the passions about making the two worlds collide, the geology and geophysics collides in these matters. Okay, shall I start the presentations? Hopefully it will take less than 15 minutes. If not, Dr. Indra, please let me know as I might blabber over a whole range of topics.
You have 50 minutes.
Good evening, Pak Wahyudi juga sudah datang. Terima kasih.
So, yeah,
we'll start. Yeah, this is the first bit of the presentations, because the title is about fault mapping. Perhaps you've seen this meme quite a few times. In geology, there are only 3 types of faults, or maybe 4 if you include your fault. There's a normal fault, reverse fault, and transform or strike slip in mechanics. So what are these faults roles in the explorations, perhaps, or in any field that related to fault identifications and mapping, for example. So there are 5 scenarios that these faults can be addressed in a way that you can use it later on, either for explorations or hazard, for making sure that you're addressing the geophysical issues, perhaps. The first one is that these structures, in terms of geological structures, controlling fluid flow. So if you're looking for structures that are acting as a permeability, perhaps, you should know what kind of structures are there, and then how it reacts when it's subjected to today's regional stresses. Secondly, you will see the structures or fractures as a storage capacity. So looking at this from the geothermal point of view, for example, some of the geothermal reserves are within the faults because the fault has been open for quite some times. It has been the major permeability pathway going from the deep to the shallow part of the crust. So it can be a storage, it can be a tank for the heat. The third one, these structures acting only as a permeability, so only as a permeability, not as a tank. So you would know the differences. One, the fractures or fault as a tank, as a storage for the resource, whatever it is. It can be geothermal, it can be oil, it can be mineralizations, perhaps, if you want to look at. The second one is fractures as permeability. So no storage capacity is there, but it controls the fluid. It controls whatever that come across it. It will redistribute the fluid across the entire bodies of faults, for example. The fourth one is how can we relate between the deformations that's mimicked by the faults and also the fluid flow. So how the fluid would be reorganized when it hits one certain surface of the faults, for example. The last one, which would be the encapsulate topics of faults and permeabilities and porosities, is how can we determine the controls of these faults versus something that could not relate to tectonics, perhaps. So if you're looking at the fractures in the geothermal, for example, not all the fractures are created by tectonics. Perhaps it created by the magmatism. It created by the hydraulic force of the magmatism. It created by the cooling of the magmas. So some of the fractures are not related with tectonics. So you should be able to differentiate them before then you could address them in whether you would like to connect it with deformations related to tectonics, perhaps, or you would attribute it to the process of magmatism. Okay, so in order to be able to look at those topics very carefully, we need to know, first off, we need to know where we are. So at the moment, we need to know where are we standing on, whether we are in the edge of the plate. You've seen these diagrams many times, whether you are standing on the stratovolcano, perhaps, or you are standing on a shield volcano, or maybe you are in Iceland at the moment, standing at the Oceanic spreading ridge, or maybe you are in Indonesia, standing in the edge of the continent where you would have lots of thrust and normal faults and volcanoes, of course, at the boundaries between Indonesia and Australia, Indian and Australian plate and Eurasia, to be exact. So it is important to see that, because then you would know what kind of tectonics are active at the moment today. Because when we address those faults and attribute it to the tectonic processes, then we should be able to link the history of the plates to the age of the rocks, to the age of the deformations, and then bring those two together to making a kind of a regional synthesis or conceptual plays, if you would like to say it, about one particular resources, oils, minerals, geothermals, and things like that. So making sure that you understand the regional sides, and then you will look into more detail and kind of subscale of local geology. So we are also using today's informations about what happens in the world as for the moment. You could use the stress field. You can Google it from easily. You could ask for today's or present day stress field in the world. They'll give you a maps of present day stress fields in the world. And then you would know where you are at the moment, whether you are in the areas that are getting away from another, which we call divergence, or subductions, where two plates are colliding, or maybe transform, where two plates are passing away from each other, like in the Sorong fault zone or the San Antonio faults there, where the American faults are moving slightly off the boundary. So you can see a big transform faults there. The important things, whether you would be able to guess where you are at the moment, is that you could place your areas in a certain tectonic positions, so that you would expect things would happen in a certain ways in that area. So for example, if you are in Iceland at the moment, you would not think that there will be a thrust fault cutting across the volcanic series in there, because you know Iceland at the moment are in the divergent regimes of tectonics. In contrast, if you are in Indonesia, you could have thrust faulting, you could have extension, whether you are standing next to the trench or you are standing far away from the trench, where we do have the back arc basins. Like in here, for example, you would have the back arc basins in the continental crust, you would have the extensional faults. But then you would attribute, you were more likely to attribute whatever happened on the crust, on the upper crust that you are doing research on, to the nearest plates, so that you would know what kind of regional arrangements that is there. Okay. For example, again, when you are in the large rift system, say I can take you to Africa, for example. This is the edge of the Africa. This is the Horn of Africa. That's what they call it. This is eastern part of the African plate now is moving to the east, and the western part of the African plate, the rest of it are moving to the west. So you could see this large rift zone that cutting across Egypt, going to Somalia, to South Africa. So you would see these lakes. You would know this one. This is Lake Victoria. This is the source of the Nile. But then people also said that perhaps that's not the source of the Nile. It could be coming from somewhere else. But you can see there the river networks committing from the Lake Victoria down to the Nile Valley and goes to the Gulf of Aqaba. As we mentioned before, in areas where you would likely to see tectonics that are divergence, for example, in these Atlantic ridges. So you could see in the Atlantic ridges, you could see where you are, say in Iceland. Oh, sorry, the pictures are slightly off. The Iceland should be up there. You know, Iceland is on the surface now, it's not subsurface. But if you could go down to the south, further down to the south, and then say, for example, you are in Brazil. This is Amazon basin there, where you would have a lot of oils in there produced by Petrobras or some other large oil players in the world. You would see the relations between the tectonics and the basin formations later. So people in early geological thoughts that these islands, the coastlines connected to these area, so then you would know if you have a resource in there, and you could also have resource on the other side of the continent, which is nice to think and then nice to see as well. Yeah. So to wrap up the first part, I would like to ask you to, from now on, whatever resources that you are going to explore, I would suggest you to think in a regional fashion. So you would think first in a kind of broad geological tectonical framework, and then you moved on to the target area to see what the local geology looked like, the stratigraphy, the structures, perhaps looking at the remote sensing, mapping, and then using tools like geophysics, magnetotellurics, or gravity, resistivity, and those useful tools that you are know better than me. And then using those two knowledge, as I said, combining those two knowledge, and then try to integrate them into a local and regional geological concepts so that you can think about what may be developed here. You know, the resources say that you want to develop an oil field, for examples. You would know regionally this basin is formed 50 million years ago. The sediments are this, and that. There are deformations at this time, and then followed by another deformations at another 50 million years from that episodes, for example. Then you would have the general tectonic frameworks to be put into a local geological perspective, so that you would know what could be developed in the areas. Being said that, and I would like to emphasize this, when you think in kind of original fashions, you would know the broad scale of things, you would know the broad scale of tectonic framework there, but then you should act locally, meaning that you need to immerse yourself in the local geological or local geoscience or geological phenomena, so that you would be able to synthesize it based on the data that you have. It is good to have a background knowledge of geology before we get into the areas, but then you would also have to be objective in acquiring the data. So the reason I emphasize this is that some of us, perhaps with the knowledge that we have, when we get into the field, we are easily being distracted by the concepts, and then kind of putting aside the data. You know that when you know about something, and then you expect things, and then you get into there, and then there are some things that may or may not be agreeable to the concept that you would have at the first place. You tend to kind of putting aside those facts just to support what you have as a background knowledge. So I don't want you to do that. I want you to be a very objective, and that matters, so that you can combine your regional your regional framework into a local geological or geoscience phenomena that you are looking at. Okay. So for example, like this is an area to the north of Sumatra. You could see this is free image coming, not free, but you can easily get it from Google Earth. This is just snapped a couple of hours ago. This is an area in the north part of Sumatra. So you can see there are some shapes that popping up. You can see shapes that popping up there, flat there, some shapes in there, and then very rugged terrain in there. And then what can you use? You can use whatever available in whatever resources that you have. At this moment, I use a terrain functions of the Google Earth, and then we can come up with a load layers like this. You can see some of the structures, right? You can see there are beddings, right? The plains, the bedding plains that are dipping towards the northeast gently, and then you have another bedding plains that are dipping to the north, to the southwest steeply. Again, you would have the same thing. You would have the same thing in the southwest area too. So using these free images, you can see it, the tectonic frameworks in the kind of regional fashions. You see what you would expect when you are being transported to the area, and let's do a work in this particular area. So what do you expect? Okay, I see a bedding dipping the northeast and bedding to the other one. So I would say this is bedding dipping that way, and then bedding dipping this way, and then you would see bedding here. You can see bedding there, bedding dipping that way, bedding dipping this way. So you would know if you make cross sections out there, you would see something like that. You would see fold, kind of like this. But then you are deployed in this area, for example, where you would say, yeah, we should see the same geometry. So this fold there, but then there's something strange. There is a lineament that cut across this area. So perhaps this is a fold, for example. So when you think about the areas, say, okay, this area has been folded by fold and thrust belt. So I would not expect another else. But then you are deployed to the areas where you would say, oh, hold on, there's another thing. There is something else other than thrust and fold belt. So looking at those two scenarios where you would see a regional geology in a framework, a tectonic framework, and then you have local geology, then I would like to persuade you to think again more about the regional geology before you get into the local geology, so that you can have a complete consideration, so you can complete comprehensions about what happened. Okay, this is a difficult one. Well, not only the students, but people who are already professionals often undermine the scale of observations. Geology, in terms of the phenomena, it should tell you in many scales that we are observing, the phenomena should be persist. So when you look at the folding in one areas, for example, in one outcrop, you would see folding in the thin sections, you would see folding in the large regional scale. But sometimes people misunderstood the scale. They would think that faults here may not be mimicked by the smaller scale of observation, which cannot be true, because geology is a science that you can see in many scales of observation. So the scale is independent. So you would see many evidence of the same phenomena in different scales. Okay. This, for example, this is a particular areas where you see a fault there. Well, not a fault, but there are many faults. You can see 1, 2, 3, 4 faults that you can pick out from the screen. But then if you look at more closely in some of the faults, you could see in one of the faults, say for example, this is the faults that are close to the guy who are sitting there. You would see those faults are actually not one line. When you see it there, it appears to be one particular line, but then when you see there, it's not actually two, it's perhaps more than one. You could also see that the geometry of the faults may be different from planes to planes. You can see very flat planar surface there, but slightly curved, slightly downward. You can see the differences. So these can tell you some of the geometry of the faults. Thus can also tell you the generations of the faults, the mechanisms of the faults. This is in thin section, so you can see the same thing in the smaller scale where you would see K feldspar. This is minerals that's been cross-cut by a fault, so you can see quite clearly. All right. Are we allowing questions, Dr. Indra, during the time of presentations?
Yeah, you have 50 minutes.
No. Are we allowing the questions during the presentation, or we can just go on until I finish and then students can ask?
Usually we wait until the finish and then
okay. That's fine.
The participant can ask, but if the participant want to ask during the class, I think it's okay.
Okay, so perhaps you could write it on the chat box, so you can we can read it later. I can finish the talk first. Well, regional things, and then some of the regional things look like this. So you could see the maps produced by people, seeing what is actually happening in areas we are studying. This is from the PostGen maps. Some of your lecturers are involved in this. They made a very beautiful map about the active faults in Indonesia. So you can see where you are at the moment, because you expect, oh, there's a large structures that coming off there. Perhaps it will affect the areas that you are studying. So how it affects, and then how can it affect, and then how can be observed. That's your job to see these features. Okay. The other one, another kind of set of data that we can use the GPS data. Some of your lecturers at the geophysics department, and also geology and also geodetic departments are dealing with this kind of things quite extensively. We can call it geodynamics because that's what people call it, but essentially we can use and we can see the data coming from these GPS stations to see the actual deformations that happening today. Perhaps if you would like to think that your resources coming from ages of geology 5 to 10 million ago, this is not really accurate. But if you are dealing with faults or fractures, that can help you to kind of extract those resources slightly going up to the shallower place. Perhaps you could think this as a supportive data, so they can use, okay, so today you would have these factors of movement going from these islands going to that directions. Therefore, if we have faults in running that directions, it could be a critical fault that you could hope these faults could be as a permeability, like that. That's one example to do it. Yeah, if you are going to explore more detail about particular resources, of course, you can use gravity data, you can use magnetic anomaly maps that can also give you an idea about a particular structures, for example. So you can pick out clear discontinuities on the map. You could discuss it, you could challenge it with another set of data, like in gravity. Perhaps the geology there has conducted field mapping. You could combine those data with a surface and subsurface and also aerial data like this, so that you could have a good comprehensions about what happened in the area. Okay, so now we are going to the main topics. We are dealing with a phenomena in geology that's called a structural geology. So any structural geology is basically structures that form after the rocks being lithified. So any kind of structures that are not formed after the rocks being lithified, we can call it the primary structures. Some examples of primary structures is the columnar joints, for example, in the lava, or sheet joints in the lava. Some sediments can also have thin sedimentary structures. You can have folding, thrusting, but then related only with sedimentary features. But what we are going to talk today, tonight, this evening, is basically the structures that formed after the rocks being lithified. Some of the structures, you can see it on the screen at the moment. You can see fold, you can see faults that are paired, for example, faults that has a shape very steep like that. Some of the fractures are perpendicular to another. That's what we call joints, for example. Then by knowing the mechanics of these structural geology or geological structures, you could attribute these structures to a more original faults, for example. Fractures, because we are going to address one particular terms in the topics, which is fault identifications. So we cannot pass the definitions of fractures, because essentially faults is basically a fractures that has moved on its plane. Yeah, fractures in nature has a fractals law. it means that it can be observed in many different scales. In geology, there's only 3 ways that you can make fractures. There are 3 modes of fractures. This is what engineering would like us to think. So there's mode 1, mode 2, and mode 3. You can look at the left side diagram to see what is mode 1, 2, and 3. Basically, there are fractures that are opens, and the other 2 fractures are moving on the planes, whether it's parallel to the face of the plane or at an angle, or moving across the plane. And in nature, there are only 3 conditions of rocks and faults. You can call it stable, critical, or unstable. So we can come to this later on, because this is another topic. What we are going to see is how can we address, how can we identify faults, and how can we see it using a geophysical data. Before you understand those things, I really need to reconfirm our understanding about faults. Any faults, we say, in every aspect of our mapping, for example, needs to have a kinematics, need to have how it moves. Is it moving vertically, normal or thrustful, or is it moving laterally, strike slip, for example? So if a geologist showing this is a fault, but then he cannot, or he or she cannot say is this normal fault or thrust fault or strike slip, left or right, you could ask his opinion later on, or her opinion later, in what sense if the fault's moving, is it normal or thrust? Because it is important to make those interpretations or based on the data, because those interpretations will lead into a more geological consequences later on. Yeah, I know you've seen these images quite a few times. This is related to the geological, so the regional geological or tectonic parts that I've been mentioning in the first part, where you would see perhaps what kind of stresses that you are experiencing, I mean the rocks experiencing at the moment in the area, whether you are in the divergence, intentional stresses, or maybe you are in the compressional stresses. So you would know that you could see these stresses where when you know where you are at the moment in relations to the tectonic plates. The other thing that could be another topic of these talks is basically the depth. So when you are at the surface, of course, there are no lateral forces. So the rocks can be easily pulled apart. It's easy because there is no lateral forces. But the deeper you get into the earth crust, then you would start to see more of lateral forces. At the very beginning, perhaps, the vertical forces is smaller than lateral forces. Later on, when you are getting deeper into the crust, where you are buried in 9 kilometers of earth crust, for example, you could be seeing a vertical stress is bigger than the horizontal stresses. So why this is important? Again, this will say to you in what kind of situations that you are dealing at the moment regarding to the faults that you are trying to map. The other one is the rock itself. It's not the rock. What the rock is cooking, not like that. So this is the rock compared its tensile strength, so the strengths that being pulled apart, and then its strengths when it's subjected to a force that's been moving close together, so convergent forces. You can see that the strength when you are in compressive compared to tensile is almost tenfold of the strength of the same rocks. So you would know the rocks can be easily deformed by a tensile than deformed by a compressive strength. So you could see more deformations in the areas of tensiles rather than you'd have more in the compressive regimes in terms of faults. Then you could look at the fault itself. You could measure the faults. You could see the actual movement of the faults. You can see the fault attributes, the directions, the slicken sides, etc. So you can record it, and then later on you could use that as a data to put it in a regional context. What is interesting about faults or fractures in general is that it started small. It always started small. These small faults or small fractures are then connected by a larger amount of strain. So for example, at the first stage, you could only see these small cracks opening because this plate being pulled away from one another. For example, this being pulled away on that side, going to that side. Slowly, as you exert more forces, so these initial fractures propagate. It grows before then it connects with another fractures. Then these two fractures becomes one. Imagine that you would have 5 sets of double fractures that combine into one, for example, and then you exert more forces, and those 5 doublets of fractures connected into one. Yeah, you start small, but then as along with the additions of strain, when you add more stresses in there, you actually end up connecting those small fractures into making a big one. That's one phenomenon that you could also see it later on in the later part of the presentations. In terms of the faults itself, so some of the faults, I would like to put this later. This is an introductions about how we can view the fault as a unit. So you can see faults in different areas. So there are things that we called matrix, a pseudo matrix, and also the fault zone. Fault zone can be divided into fault core, and then inner fault zone, outer fault zone, and you could see the relationship between the areas of those faults and the zones itself to see whether you could map out the relationship between the areas. Say, for example, if you see a fault core 5 meters wide, how much the total fault zone that you would expect? Some people already dealing with those things, as we are also doing the same thing at our lab in geodynamics and sedimentology group. So we are trying to map out the faults with the fault cores to see if we have this wide of fault cores, how wide is the damage zones, to see whether or not we can quantify the areas. And then you could see, okay, these areas has more fractures, and therefore you would have more probability to have a permeability in there, things like that, that you can kind of exercise later on. Yeah. Okay. There is another thing that we called in the faults and its relations to the fractures is a terms that we call a percolation threshold. As threshold should give you an understanding, it means a limit. So these fractures can be a beneficial unit when it hits the percolation threshold. It means that before the faults or these fractures are connected to each other, it will not be useful for us. But when we can identify the faults are connected to one another, then you would know how many connections that we need before the faults can be determined as a moving probability. So when we were having a probability in there. Okay. This is some of the image that you may see. Well, this is you can easily go to Google to see some of these image, which is very stunning. You could see some of the fractures, some of the faults perhaps in the areas, and compare it to an area next to it. This is fun thing to do. So look at this side where you would see one directions of fractures that's been intensified by weathering. You could see the sand here, these ridges, very thin and narrow ridges. And you see, look at that, it's only one set of fractures. On the other side of the valley, you could see multi directions of fractures. Okay, so when you're working in one particular area and say that your area has the most complete geology, for example, and then your friends moving to the areas perhaps not only is only 5 kilometers away from yours, and then they start seeing, no, look, this area has more faults cutting across it. So how can you justify that? How can you see something like that in a very short distance, whether you can see, hold on, what is difference here? You could see that this whitish unit is placed above the reddish unit there. You can see this is covering the red unit. And how come this unit has more set of fractures in there? That's something that you your geologist friend and you need to think about, and need to think about these implications about the resource that you are trying to get in the areas. So what controls the fractures? First off, in lithology. So you need to know the geology of the areas, what kind of stratigraphy that you are dealing with, whether you are in volcanic zones or in the basins that has 7 kilometers of sediments. You would expect more various sedimentations, or you are at the edge of the continent where you would have thick passive margin series, for example, so quite homogeneous rocks with only little partings of limestones. So you would know the areas that you're working on, and then you would expect, okay, if faults are going through these areas, what would happen? And then the other ones is, this is some examples. You could see different rocks with fractures. One has more fractures than the others, just like image that you've seen previously. The other one is the geometry of the structures. You would see more of the geometry later on. You could say if the faults containing a breccia, big size like this, or maybe the faults are only containing these small strands of an echelon fractures. Yeah. Like this, for example, you could see this is normal, and the other side is normal, but on the middle part of sections, it has been cross-cut by fractures. Later, maybe we can discuss this later on, but the positions of the areas that you're in, for example, you could see differences where you are sitting at the crest of the fault, and then compared to the areas where you are perhaps maybe sitting on the flank of the fault. The structural trends will be different, the patterns will be different. Can you connect those two? Yes, you can. You cannot do that unless you would have the original overview about the geology, so that you can connect those two phenomena when you are observing in particular part of the structures or the other part. So when you are standing in there, where you'd see more of the strike slip going like that, and then when you are standing in there, where you would have strike slip going the other way. Hold on, these two areas are very close to one another, but then how can they be so different? Right, so we're going to the structural mapping. Remember, fault mapping is not the same as fracture mapping. Some of us got into the mud pit by saying that when you are trying to map the structures, you only need to map the fractures. So you would need the measurements of lots of fractures, so then you can see the faults. Think of it like this: when you have a movie, when you watch a movie that has a big star as a main star, for example, so like Fast and Furious. So you'd have one Dominic Toretto and then another 7 of his friends. So when you are following the series, or because it has 7, maybe 8 series of movies, you could see the stories evolve, and then towards the end of the series, you would start to say, hold on, which one of these series is the main star? Because it appears that they are all important. Some people forget that in concert, so when you think you are going into a concert, say concert of a music concert like Paddy, I like Paddy. Before Paddy starts, the organizer will give you the indie band, for example, for the opening. Sometimes the indie band so good, so that when Paddy comes up to the stage, you are saying, "Oh no, this is just the usual." You lost that excitement. The faults and fractures are pretty much similar. So people tend to observe fractures in the field than a fault, because then people would say, okay, there'll be fractures in there. I can measure a lot of fractures. Then I can interpret what the faults look like. That's the wrong thing to do. So whenever you are going to the field, with the geologist or not, make sure when you are trying to map those fractures or faults in these terms, you should map the main star, which is the fault. And there will be the co-star, the one who are not that important, but without those not important features, the faults cannot be explained perfectly. So remember, the fault mapping is different than fracture mapping, especially when we are mapping with a geophysical tools. So you cannot be mapping a small scale fractures, right? What you map is basically a fault. So you would have to know what kind of fault is that, and then combine those data with the field, with some other surveys, so that you can map out the areas in a considerable way. So you can see in maps, you can see a fault running like that, or in the cross section, you could see faults going like this, and another one, perhaps the faults are going like that. You could see it on the surface, but how can we see it in the subsurface? That's a good starting point, where if you'd like to think about what kind of faults that you are mapping at the moment. Yeah. Okay. In order to be able to map carefully of the areas, make sure, again, or to reiterate this, you would need to know where you are at the moment, because then you could decide, or you could think about the structural style. So if you are in Iceland, you would expect the normal faults, because this is a mid-oceanic ridge, so perhaps the normal fault is not very steep. There will be a dip somewhere, but you would have two normal faults facing against one another. Things like that. So you would expect then, okay, what sort of geometry that we are looking? Are we dealing with one large fault, or are we dealing with some of these smaller faults that are now trying to merge into a large fault, for example? The variations of the structures combined with the overall geology say that you would have normal faults, but then you would also complicate the geological process by adding magmatic features in there. You'd see dike. You would think, well, when does this dike cross-cutting the rocks? Is it after or before the grabens fall? That is important in order to be able to map carefully. And some of the features can be very specific. So remember, this is a topic, a very wide topic about structural geology. I would not be able to explain it one by one. I would like to address the probability that we can have a very particular features in one deformations. Some examples, one examples is that when you would have two contrasting lithological units, one is strong and one is weak, then you would see a features that you would not expect it, where you would have faults. When you say faults, this is when you have normal faults, you know that the layers will be cross-cut by the faults. You would see layers being cut, so it means that it's separated. But then if you complicate the geology by having two separate layers, which has strong and weak properties, you would see something like this. You would see the stronger rocks being cross-cut, but the weaker rocks is playing along with the faults very nicely. It can add to the uncertainties in the field. It can add to your comprehensions of the areas. You could see it later in the later stages of the talks. Well, I'm going to show you now the accompanying secondary structures as we know it. You've seen this one before. There are secondary structures that related to faults and fractures in general. So you would see joints, you could see shear fractures, stilolite, vein, and etc. You got it from the lectures, right? I'm not gonna explain that anymore. What I can show you is some reviews of the shapes of the mechanics of things that we are looking. This is the first one. This is joints. Remember, joint is a very general terms. You should avoid it if you don't know what it means, because then people tend to correlate it with something else. This is also a joint. This is what we call joint with a ball inside it. We call it ball joint. And this is also joint on human bones. And you can also this one. This is joints if you are if you have the opportunity to go to the UK, for example, for your master or for your doctoral degree, you would know that this is also joints. This is, well, you can see that that's marijuana. There's being folded as cigarettes. They call it joints there. So make sure, this is my message, make sure that you know the terminologies. When you say something, you know the terminology, because joints is a very broad terms. Joints in kind of geological sense that we are talking about can be related to many things. It could be related to cooling joints and roofing when geological units being brought to the surface, perhaps related to faults, or maybe to fault. In general, joints could be formed because the crust are trying to accommodate general adjustments. Joints means that we have a planar structures with little or no movement. So visually, we cannot see a movement of the fractures. So it means when you have rock like that, joints looks like something like that. Sorry, I'm got too excited. Means that joins me looks like one line cutting across rocks with no particular movement that you can see it from there. Difference than when you have rocks like that, and then you would have an opening like so. So you would see an opening of the rocks like looking like that. So it's not a thing that you can see opens like so. So joins, you can just one line. When you see your book, or yeah, you can see a book, for example, you close the book and the layers forming a lines, you cannot see any displacement of the layers. The joins is pretty much like that. Okay. The second one is that we have extension fractures, which is slightly different from the joints. It can be related, it mostly related to tectonics, and it can be filled by a fluid to becomes vein. Could be related to fault, could be related to faults. We can see directions of the least stresses if we can see one of the extension fractures. So whenever we can see an extension fractures, for example, this white one on the right side on the bottom of diagrams, where you see white vein cutting across vertically of the tiles, you could expect that the least geological stresses coming from that directions, because it always opens in the directions of the weakest geological stresses. Yeah. And then the other one is shear fractures, where you would have a pair of fractures that we can use the acute angle of the pairs to see the maximum or the largest stress in geology. I know this is perhaps yeah, you've seen this many times. What does this importance? Well, the importance is that faults, as I said at the beginning, faults are mechanically fractures. So you would know that these faults are basically the same thing that you are looking at the moment, but then you're looking at it in larger scales. So you would expect, okay, this fault is normal faults. What kind of normal faults in there? Are they related to extensional structures like that, the previous one, or maybe the shear fractures that we are looking? So it is important to revisit your knowledge about fractures. So this is the example of shear fractures, and then specific arrangement of the vein. This is an echelon arrangement, where you would have an echelon like that, where you would have a shear zone coming across on the directions to the left. This is causing these arrangement of fractures. So these features can give you a major hints about what happened on the subsurface. So you can see, okay, this area has been deformed by the shear zone. We can call it the shear zone. Yeah. Okay. What is interesting about these fractures are they often have friends. Well, they are friends with the faults are the fractures that are the same directions, or the fractures that has the same orientations. Okay, so these, we can call it one fracture set, and then the other one is trending like that, and the other one is trending like this. So in the pictures that you've seen at your screen at the moment, you could see there are at least 3 fracture sets. Later on, you would need to define which are coming first, second, and which one coming last. To add to the interesting topics of the faults, faults often also have linkage. This is the same topics which I would like to take on later on when we talk about the fractures or faults being formed as an individual fractures at first, before it goes grow on the tip, and then it can combine into one larger faults like this. So it can link. So how can it link, and what sort of geometries that we can expect when in the two faults are being linked to one another? You can see it in the later presentations. This is mud crack, so you could see it on the surface of the paddy field when it's when the farmers finish the crop, and then sometimes the paddy field being abandoned for a couple of months. You can start seeing some bog or swamp being filled by mud, and when it comes to dry season, those little swamp can be very dry. So then you can start to see these mud cracks. Fortunately, we can see this mud crack displaying what we call a fault linkage. So this is one particular fault, and then that's the other one. So when the cracks getting bigger, so these two faults are trying to link to one another. This is interesting topics, because then you would see when you map something, you can see two faults merging to one another, but then at different depths, it can be very different. It can be the faults are totally different because it's not connected on the shallower part, but it's connected in the lower part of the crust. Some parts has geometry like this, where you would see faults creating a space, a particular space that we can call a pull apart basins or transtensional areas. So these space can be filled by hydrothermal fluid, so that you can have a special shape, rhombohedral shaped vein like this, which could be filled by gold, for example. Or you could have fractures that cross-cutting to one another. I know this is perhaps too detailed in terms of geophysics, but you can see it later on. How can your understanding about these patterns, these attitude, these phenomena of the fault and fractures can help you into determining what kind of structures that are cross-cutting your areas there. Okay, this is a intermezzo image. You can see fault there, vertical beds. You can see folding there being cross-cut by the faults, a very complex area. Some of the geometries that you would expect from the faults, although maybe on the seismic data scale you wouldn't be able to see it, is that these breccia zone, this brecciated zone, this is the proof that one unit of rocks being squashed. So you started to make you pulverize the materials within the fault zone, and you end up with these breccia. Some of the breccia you can see there being filled by the hydrothermal fluids. It means that when the faults are moving, the faults can be a very prominent permeability. So that because these fluids coming across to the fault and then being transported from there. You could also see slickened sides in the faults. When you see these plane with lines that you can see, you can measure the lines, you can give the actual fault movement. There are some more examples like this, very beautiful one. You could basically measure these data, and then no matter how small the fault plane, if you can measure it, it will be useful for a local geology and then for regional geology. So when you are mapping with your fellow geologist or a geologist, you are features, make sure you're not passing it by. Make sure you are measuring it, because this is the star. This is the main star of the movie. So make sure you are not neglecting it. Make sure you measure it, because this is the main star. This is the Raisa. I like Raisa. She sings quite well. Sorry. Yeah. Now we are looking at the anatomy of the fault. You've seen at the very beginning where people are trying to divide the areas of the faults, fault cores, damage zones, and etc. When you look at the faults in a cross-cutting senses, you would see an areas where you would call a halo areas. This is what we call halo zone. Halo. And then at the very center of the fault plane, you could call it a core. And then you could see an area outside the core, is marked by slightly purplish color. This is what we call the damage zones. People often refer faults with the terminology of the damage zones. Yeah, so when you say, oh, this fault has a damage zones, it means that it has the fault core and then the areas away from the fault core to a certain width that you could see a development of fracture sets or fractures networks. You could see many examples in fault damage zones. You could see areas being disrupted by a multitude of fractures, or areas being disturbed by one large fault with many strands, for example, or perhaps not a particularly clear fault plane, but you would see lots of fracture zones in the area or fractures damaged area. So you don't really see the faults, but then you could see, oh, what's that? There are so many fractures in one part. So when you look at the field example, this is what we can see in the fault damage zones. Look at this beautiful example from a marble field in Italy, if I'm not mistaken. This is published by Grunelade 2006. You can see a fault zone here. You can see a core of the faults running across this field. You can see the differences between the fractures in this area, that area, compared to what you can see in the middle. In the middle parts being squashed by the fault, so you could see more fractures in there. That's why people often to differentiate the areas like people did on the previous diagrams. This is the damage zones. This is the background areas. This is the pseudo matrix, as they call it. So that you can expect about having these areas that's being controlled by the fault zone. Okay. This is some of the schematic drawings of the fault, looking at the initiations, the propagations, the fracture arrest perhaps, and the cluster formation. So some areas, imagine if you have a plane that is vertical like that. So you would have moved on this plane vertically. So you move like that to the other side, maybe it's just a slight slip. Then you end up with the very narrow zone. Compare it with when you have a plane that is tipping quite gently like this. Then you would end up with an area which is wider, because you when you have something vertical, you basically are moving in those areas only. But when you have something slightly slanted like this, the areas being deformed, it's not only the fault but also the areas above it, the hanging wall. So you would say the hanging wall in the case where the fault plane is slightly dipped like this, the hanging walls will be deformed more than the footwall. So those kind of anticipated deformations in the structures that you are looking can be very valuable knowledge on what we are going to see. We can see this is also seeing the damage zones where we would have a large displacement. You could see a large damage zones, wider damage zones. when you see smaller displacement, perhaps the damage zones are also smaller. Some people are already dealing with this. They calculated the width of damage zones with the length of the faults, so that you can kind of predict if we have faults this long, you would have this wide of damage zones. What I most like about fractures is that they have what we call a relay zone. A relay is an area, remember where I show you the mud crack in the paddy field? You'd see one fault going like that and the other fault going like this. When they're trying to merge, before they merge, they create a zone here in the middle that we can't call it a relay zone. This area can be very important in the distributions of resources. Say we are in the African Rift today. So you would know that these floors are starved from sediments. This floor is not starved by sediments because this floor will have a sediments coming across from that directions compared to this floor of basins. By looking at the distributions of the faults and its relay ramp, we can predict which area has more sediments. That in itself is one great insight about looking at, okay, which area has more thick sediments, for example. Look at its relay zones. One starved basin wouldn't have sediments in the areas where you look at, okay, this is perhaps sediments not coming from there, because sediments not falling over from this part. Some sediments could falling over, but not many. Some sediments coming laterally. So this is quite important. With some examples of the relay ramp, you can see the networks of the faults. This is from, forgot to write the authors. Perhaps this is from Fossen, 2011. I apologize if you are trying to find the resources. This is from Hakon Fossen, 2018. You can see the networks of the faults. There are faults that are connected, just connected, and it creates a relay ramp on that side there. Some of the faults are already connected, and it creates a very, I would say, unusual, because if you learn about structural geology, then you would learn about the arrangements, right? So you would see normal faults going like that way, normal faults going that way, connected by this transfer zone is something very peculiar, just very interesting. This is facts, by the way, so you need to kind of interpret it later. But the facts looking like this, so you'd see faults being connected to one another, and it creates an adversity in the maps and in the areas that you are mapping. This is the kinematics or the mechanics of the fault relay zone formations. You can see smaller faults trying to combine to become larger faults, like so. And then at the end, these smaller faults are combined into one large fault and create the faults that you would call a border fault, for example, the basin margin, or any other types of fault that in size. Make sure you understand that those large faults are started small. Yeah. When you look at this relay ramp, there's one more importance other than the sediments that are coming off from the relay ramp. These areas of relay ramp is allocations of a future breach, allocations of a compromise between the two faults. So this relay zone can be allocations of compromise between two faults. It means that this area will have more permeability than the other part, because it has more fractures that are connected, cross-cutting between another, passing the percolation threshold like you saw before. So these areas can be beneficial. Yeah, at the end, these two faults can be something like that. So it connects in that side. When it connects, the strain are now shared between the two faults. Before it connects, this fault carrying particular strain these faults carrying particular strain. When that fault's connected, so the strains now being taken care by the same fault because they are now at the same fault. Looking at some of the faults, perhaps you would see faults that are not really clear about what it's related to. Some faults showing folding like this. This is fold related to the fault, so a fold related to fault. Some other faults showing a normal displacement like this can also produce folding. So it is important to know your basics about the geometry, the style, the shape of the structures, so that you can expect the structures, the actual structures that you are looking at. Yeah. This for examples. This is sandbox model from Professor Sapi, Benjamin Sapi, from our group. You can say you can also look at the comparisons between your models to what actually happened there. You can see the faults. Where's the fault now? Fault should be bordering a unit that can be seen thickening towards a particular plane. So you can see that fault there. Some faults are placed away from the border fault. This is what we call the border fault, the main fault of the areas. Some faults are away from the border fault, but carries on importance similar to the border faults. We can call this because it originally it goes like that. So the pink layer there, it should connect like that. But then because it's been stretched quite away, so it started to create structures, what we called a crestal collapse structures. This is very common when you are dealing with normal faulting. You would see crestal collapse structures. Yeah, you can combine it and see whether the planes can be very different. This is listric plane curving fault. This is planar, which is flat. You can see the effects of the deformations. This is similar strain, by the way. So it's been stretched out by similar distance, but then you can see the differences. There are less rotations in the areas where you would have a planar fault like this. So this area is smaller compared to what we can see in the faults that's being led by the listric faults. So the geometry is really important. When you look at your seismic data, make sure that you can see the geometry, whether is it flat, planar like that, or curving. So this is some of the examples that you can see. You can see this is being a planar fault. Yeah, you can see this is flat fault. You can see that's the differences compared to this one. Yeah, so this is creating something like that. Maybe like this. Is it different? Can two different fault planes occurs in one place? Of course it can. You can see this being curved like that, and some of the faults are planar at the very top, like so. Yeah. Some of the geometries that perhaps you would not be able to see is something like this, because this form slightly deeper in the crust, but you could have this when the sections here being exhumed to the surface. So later stages create this to be exhumed to the surface, then you would see the geometry of what we call duplex, extensional duplex. More often, we are seeing this kind of fault. So you have imbricate normal fault like this, being yeah, you can basically see it in the data, similar to that. The previous features that we've seen is a style when we are dealing with a normal faults. What happens if you are dealing with thrust faults? This is what you can see. You would deal with faults that are not really clear, because more often the faults are subhorizontal, so near the dip of the bed, and then it can be confused by the beds itself. So sometimes you don't see the faults. You can see the defaults by the predictions that you have looking at these faults, because there will be no faults without faults. So every time you see fault like that, underneath it, it must be a fault. You cannot see it quite clearly in there, but you could predict it. Some of the faults are quite clear. For example, on that one, it's quite clear. But in the areas where you don't really see the faults, you could see it by looking at the fold on top of it. So you can see what kind of faults are there. Another example is things like this. So you can see fold in there. The faults are not really comes out to the face, but you can see these layers being cross-cut by another faults, that you can see the faults being going on as the one interpreted on the lower diagrams. When you look at the strike slip areas, you would see something else. You see something different. Looking at the mechanics of the faults, remember when we looked at the Andersonian type faults, your normal, thrust, and strike slip. Strike slip is the only fault plane that can be vertical. So the only fault plane that can have vertical planes is strike slip. So often you're seeing strike slip being this vertical. So when you look at faults being vertical like that, most likely you are dealing with strike slip. So those styles are very different. You look at the normal faults with its relay ramp, it has a connection between one fault and another. You would see faults are dipping quite gently. And then compare that to the thrust fault, where you would see more of the folding rather than the fold. The styles are very different. When you compare it to the one you're looking at strike slip, you can immediately see why it is different. Because mechanically, this is the only impossible fault, the only possible fault that can bear a vertical plane. So you could see that. We need to be very careful though when we are looking at some of the data, that maybe what we are looking can be misleading. So some of the faults, like this, for example, so you would have flower structures from the strike slip, so vertical faults like this. When you look at the basin with a prominent basement, maybe at the very top, very close to the basement, you would see faults that are subvertical. Going down to the bay slightly deeper, it will gradually goes shallower. The dips go shallower. When you look at more examples, like in the positive flower structures, for example, positive flower structures there, if you looked at only this side, you don't see anywhere else. It started to look at the possibility of having the same deformations in the thrust fault regions. So make sure you see the whole data when you are looking at particular deformations. Don't be too excited, and then because when you are looking at and being too excited, you tend to forget the other part of the story. So you are more concentrating to the part when you say, okay, this is maybe strike slip. Why? Because it is vertical. So when you're looking on that part. But if you look on that part only, yes, perhaps it is a subvertical fault. But then the data that you're looking is larger than that. And you see, oh no, actually, maybe this is not a strike slip. It could be a normal fault. And this is being a part of a normal fault. So make sure you are looking at the complete story of things in the areas. Yeah. So this is one example where you would need to be very, very careful about what is happening here. Perhaps you would see a vertical fault plane there, But then you will see another one. It's going like that. What's happening here? Is it this one is different than this one? Does it have two episodes of the formation? Perhaps this one first and then cross-cut by this one? What can be certain in the area is that this latest fault, the one that I just point out by the arrow, is today is cross-cutting the sea surface, the bottom surface. You can see the sea floor is being cross-cut by the fault. So it means that this fault is much, much younger than the faults in the basement. So it could have two different ages of the faults. So when you look at the geometry, like what we did in some of the previous slides, you can see different faults, different geometries. Although it is the same normal fault, but when you have flat planar fault plane, it has different geometry when you have the curved Listric fault plane. So those things that can create more variables in your interpretations are the most useful things for observation, so that you can see it, you can compare it, you can challenge it, and then you can determine it to get the full story, the full extent of the story. This is another example, so you can see faults vertically, perhaps going like that. So when you look at this, maybe you look at that one, or is it something like this? Or maybe just simply like that. Which one is it? Yeah. So again, you need to look very closely and passionately. Okay, so now this is the last part of the talks. I'm going to ask you around the world. So I'm going to pay you for a ticket going around the world to see what was my talks about looking at the regional scale and looking at the local areas. This is the first one. You are being carried to the island of the São Miguel. I don't know if I pronounce it correctly, but it should be in Portuguese. This is a Portugal-owned island, so owned by Portugal. So when you are asked about, can you map about the structures of the areas? Can you do mapping in there? Hold on. How can we map here? Maybe we are using the obvious, like this. Oh, maybe we can see like that. Oh, there's one large part in there, and then what is this? This has a lot of round shape. Maybe that's a volcano, maybe small volcano, I don't know, but it seems to be fall in line. It seems to be going in that directions. Is this right? That's when you don't know anything about the regional, you started to putting all your random knowledges into one spot. Make sure when regional senses. I'm gonna take you into regional senses. This is the interpretations. From the cinder cones, and there are some faults coming across that directions. But why does this island has this kind of set of structures? Yeah, because it's there. It's at the edge of the mid-Atlantic. So this is mid-Atlantic, and then this is being cross-cut by the transform faults that cross-cutting the Atlantic ridges. So these areas is based to transform faults directed northwest southeast. So it is quite similar to what we are looking at here, northwest southeast transform faults. So make sure you are looking and then knows the regional about the areas before you are doing anything else. Yeah. Now this one. This one is, I got a hint here. This is the Caspian Sea. So you can see the structures coming across there. It goes out like that. It stopped here. It connected with another one. So this is a strike slip. This is what we call the Great Anatolian Fault in Turkey. So it's really big. It's cross-cutting the city of Ankara, where many millions of people live there. It's very dangerous. Therefore, they put a lot of seismometers around the faults to map its activity to this day. Yeah, you can see it differently. This is slightly different. This is closer to us. You can see this is Sarula, this is Tarutung. Perhaps some of you from North Sumatra, where you see this is a 1 or 2 strands of the Great Sumatra Fault. This is one strand, and then that's the other one, and this is another strand coming across in there. So it has to be like 3 fault strands creating a pull apart basins in the middle. By looking at the regional scale, you would guess, okay, this is Sumatra Fault, many segments trending northwest, southeast. I would expect you would have valley or transitional basins, lakes that are having this some sort of rhombohedral shapes, because we know the regional geology. And then you kind of shapen up the local geology by looking at more detail. Some areas look like this. How can you map structures in here? Well, luckily, you can now get to see an image produced by Google Earth in a very, very amazing way. Look at this image. You can actually do this on your desktop to see the shape of the folds very clear, even to compare it to the outcrops that you can see on the field. Before you even go to the field, you can see what kind of deformations there are there, how many deformations that cross-cut the areas before you even get to the field. So before you use those fancy tools, you know what you're dealing with. This is another one. This is from Tibet. You can see the strike slip cutting across particular areas there. This is, you can see syncline there, anticline here. You can see another strike slip there. Perhaps you can see thrust fault cutting across here. Yeah, you can see many structures there before you do anything else. Just a nice thing to do. And you can also see this. This is in East African Rift, where the previous image, remember when I show you the eastern part is going to the east and western part is going to the west. It's now dividing Africa into 2. This is the East African Rift. You can see something like that. This is the fault, one particular fault. That's the other one. And it's creating a relay ramp. This is the actual relay ramp, which is very nice. So remember, if you have river, so river is going across there, coming to here, going to there, going to that, and then it's deposited sediments in there. Can you see it? You can see sediments being deposited in there, not in the other part of the basins. It is important to see the geometry of the faults before you do anything else. Yeah, because this can be very, very useful. So I'm gonna zoom out this image in the next slide, which I think is very interesting. You can see this is in different depth. This is the deepest part, 1.5 second. You can see these faults are 1 actually. So this it used to be 1 and 2 fault, used to be 2 faults there, but it's connected already at depth of 1500 millisecond. If you look at more into a shallower sections, the boundaries start to diffuse. It doesn't really connect, if you like to say it like that. And then if you like to see it in the shallower areas, you should start to see the planes are slightly wider And then you can see some more smaller faults offshooting from the main fault, things like that. So it looks like it's no longer connected. And then at the shallowest depth, you can see the faults almost two different faults, right? What my point would like to, I would like to raise my points here is that at different depth, you can see changes like this. So when you see two faults are different at the surface, it could be that at certain depth, they are connected like this. So when you are thinking about this has one particular planes, for example, or two particular planes, remember that these two faults can be connected the subsurface or even in the deeper part of the surface, so that you would think, oh, this could be one fault and it could bring up its individual roles at certain depth, which is very interesting phenomenon to see. Yeah. And then with the latest technology, you could use many manipulations of the data. I would say manipulation is not a negative thing. You could use the data, you could manipulate it a certain way that can address certain issues. This is the data, this is a seismic cross sections, and this is the 3D cube of seismic. You could see this fault there. There's a certain fault with a very small slip. It's not cross-cutting a huge whole wavelength there. I think wiggles not being cross-cut fully. So you can see these faults being developed like so that you can see. You can see the faults are consist of 4 at least individual, 5 with this one. So there are 5 individual faults in there that you can see, which are not joined together yet. But as you extend more stress on that area, it starts to kind of combine each other and it will end up into one particular fault, just like this one. So these areas, you can see a particular fault plane. Perhaps it can be created by several fault planes at the beginning, and then it will end up with one large faults. So this fault plane, and another one can be cross-cut by another one as well. More fancy tools. Sometimes people neglect the qualitative interpretations. When you have an automatic interpretations, you would come up with something like that, for example, and then you will be puzzled by some of the interpretations like this. When you have two faults being cross-cut one another, there should be an effect of one fault being cross-cut by another. While in this diagram, you wouldn't see any effect of that. So the machine cannot tell you what happens between those two faults. Are they connected at the subsurface or not? Or are they cross-cutting between another? So it means that one is older than the other. So you will still need the qualitative geological interpretations to it before you leave it all to the machine, doing all the automatic interpretations like this one, for example. It creates an automatic fault interpretation based on the attribute. You can see some can be interpreted quite nicely, but then it starts to raise some questions about how can this one fault being branches into 3? How can we see that? This is one big one fault, or this is actually 3 faults at the beginning becomes 1. I know this is sounds speaking, oh, well, what's the difference between 1 and 3 faults in there? But if you are a oil company trying to develop a field, when you have 1 fault compared to 3 fault, it means that if only 1 fault, then you can develop 1 areas with 1 large pools of resources. But if the areas then proven being cross-cut by 3 faults, it means that you would have 3 areas being compartmentalized by 3 different faults. And that will be different in the economics, that will be different in the cost, that will be different in the times, etc. So it's early judgment that is very important can get the economy of certain companies. They would think, okay, this is worthy of development because we know certainly that this is one large structures carries on by one large fault, rather than this one large structures being cross-cut by 3 other faults. So we would have to develop 3 fields instead of 1. That could be very different. Okay. I think this will be my last one. So when you look at faults, remember what I stated at the beginning. Faults, as in fractures, as a mechanics, it is fractal. Fractal means it appears in every scale of observations. You can look at it from the outcrop scale, like so. You can see the relay ramp, which is nice, isn't it? You can see a relay ramp really nice in there. You can see the actual evidence of relay ramp. When you look at it in the larger scale, you can see a fault that is clearly cross-cutting beds, well, a series of beds like so. So you can see the faults that look like here when you have geology and the faults cutting across like that. So you can see the evidence that also shown on the surface of the earth, which means that, okay, that it could be happening, it could be exist somewhere at the deeper part of the areas too. And then when you look at the subsurface, looking at the seismic, you would think why this area has more faults compared to the other. What happened there? Could it be a combinations of 2 faults, for example, so that you'd have more fractures in there? You could create a relay ramp. And but why the other part of the areas like this, for example, only have faults at the furthest a certain depth? It's not going through the deeper sections of the seismic. And when you compare the unit above here and compare it to the unit below it, it's also very different. So there's so many things that you need to kind of think about when you are going to map faults and relations to what we are going to see in the field. But as I mentioned in the first bit, so if I would like to conclude the talks, first one, you need to think regionally and then act locally, looking at the faults objectively, looking at the map objectively. So make sure that you're not missing anything. Although you know something about the areas, you make sure that you're not missing anything so that you can see what can the actual data can help you in terms of interpreting the regional geology of the area. So I think, let me see. Yeah, that's the last slide. Secondly, I'd like to conclude that make sure you are looking at the importance of the actual fault plane, because it has geometry that is different. It has the anatomy of the faults that you can see quite different when you combine it. A vertical fault, a slightly dipping fault, a normal fault, thrust fault, strike slip, they have all different geometry. So you would know how to interpret if you know an area is, okay, this is look like an area is being deformed by a normal fault, so that you know, good, maybe this is the shape of the normal faults. It can be planar, it can be curved. Depends on what you're looking at. The crustal collapse, for example. Oh, this is a very narrow crustal collapse, so it has less rotations. Perhaps it will be a planar fault plane rather than listric fault plane. And then the third one is when you have the secondary structures with a lot of accompanying structures, the secondary structures that are not quite visible, but you'd have accompanying structures, still make sure you are not missing out the main structures. Those accompanying structures like the extension fractures, vein, shear fractures can help you actually. But make sure if you see slickened sides, you can see displacements of the faults, those are the real fault indicators, so that you can compare it to when you are working in the areas where geologists mapping on the surface and geophysicists providing data for the subsurface. Make sure you ask those questions. Are there fault in the areas? Can you measure it? What's the measurements? Where are those? So that you can correlate surface and subsurface in order to be able to integrate those knowledges, to be able, well, to make use of those data to your aims of studies. For explorations, for something else, you could choose that. But if you're not doing that, then you are missing out a lot. I think I would like to close my presentations with that point. If you're not doing in the right way, you will be missing out a lot about the explorations. You'll end up with more questions rather than answers. So I'd like to thank you all for listening to me during this late night, late evening talks, and I'd like to entertain any questions you would have. Thank you.
Thank you very much, Dr. Alvan, for the very interesting lecture. Now we will open the discussion section. So for every participants that want to ask something, you can raise your hand, so we can allow you to ask directly, or you can write your question in the chat box. Okay, there is already one question from Ramadhani. Mas Alvan, can you read in the chat box?
Yeah.
And you can answer the question.
Yeah, I think she's the one who helped me with the engineer certificate as well. So yes, I'm still interested to answer your next questions. I'm still interested. I haven't done that in a while because the load's been really overwhelming, but I will do it. Okay, to answer your questions. The passive margin boundaries as well as petroleum system Gulf of Guinea, Africa. Okay, what is the difference between passive margin plate boundaries and subduction zone that happens on areas in Indonesia? So I shall just draw a cartoon to give you some illustrations. So when you would have, generally you would have continental plates like that, and then you'd have an oceanic lithosphere. This is continental lithosphere. This is oceanic lithosphere. This is continental. This is oceanic lithosphere. Yeah. Okay. So passive margins is basically where we would have an area at the edge of the continental margin in here usually that before it goes into the oceanic lithosphere, it will be a large basinal areas there. So you would have very thick basins on there. And the uniqueness of the passive margin that it is a very vast areas. So at the end of these passive margins, you could see a mid-oceanic ridge usually. Yeah, so you'd have another plates on these areas there. Yeah, something like that. So this is the mid-oceanic ridge. Yeah, sorry if my mouse drawing is not quite okay, but I guess you get the idea. This is where the magma is going up to create new crust. It goes that directions and goes this direction. So it separates from one another. So imagine that you are in the South America. This is Brazil. Yeah, and this is Nigeria, where people have said that these two continents were once before. It was divided by the Atlantic mid-oceanic ridge to become two different continents. If you have passive margin there, certainly you would have passive margin here, because at the edge of continent where you have vast areas of continents, you're shedding materials coming from the core of the continent going into the basins. So the materials coming from the core of the continent going into the basins. This is where the areas you deposited lots and lots thick and very thick of sediments. This is what we call the passive margin. The margin where it is passive because it don't have any subductions in there. It doesn't have any earthquake. Well, there will be earthquake every now and again, but it doesn't have any subductions because it separates from one another. In West Africa, in Nigeria in particular, it has been known widely that Nigeria is a very desirable areas for explorations. I think, in fact, one of the biggest passive margin oil province is in Nigeria, because it's very vast. I should give you this, and I go to the earlier slides where you can see the world map. Sorry, I should go escape. Discard. Can still see the screen, right? Look at this one. Is it now full screen?
No, not yet. You
No.
Okay. You stop the screen.
Let me do that. Share screen. No, it's gone there. Okay. Can see it now. I hope. Look at this. These vast areas. Oh, sorry. Oh, there it is. We can see this is the cross section that I would like to make before. Apologies for the low quality of the cross sections. That's the passive margin. So imagine you are at the continent where everything is rising and everything is being eroded away and being washed to the basins. Where is the basin? The basin is often at the edge of the continent. That's why an area of passive margin there is an area where you would expect very thick of sediments coming to. So when you have thicker sediments, you have more probability to have source rock, reservoir, and things related to petroleum. Compared to what we have in the subduction zone has two phases. First, the outer arc, where you are facing the trench, you most likely related with thrust fault, lots of earthquakes and sediments coming from the volcanics. And the other one is what we call the back arc. The back arc is basically in areas behind the magmatic arc where you would perhaps create some small basin or relatively large basin like Central Sumatra basins or South Sumatra basins. It could be quite big. Then you would have an area this big being filled by sediments coming from both directions. So when you look at the environment are different. Here, the environment's being influenced by two different regions. One is the continental coral, the other one is the magmatic belt. The other one is simply the continent shedding a lot of sediments getting into the basins. And imagine this is when you have an area like Sumatra, for example, you would have Central Sumatra basins, you have South Sumatra basins. The size is limited. You cannot have back arc basin as long as the length of the island, because you would know the faults are basically starting small. You wouldn't have started to have a very large basins at the beginning. You would have to start with small ones compared with the edge of continent like this. Look at that. That very area where you would have at the end of the continents, where you have these areas, this is high areas, that's high areas. And when those areas being up to the surface, being exhumed and then attacked by waters, by winds, by another erosion agents, where do they go? Where do the sediments go? They go up to the shallower area, to the lower areas, and then where they are filled, they're going to the basins. That's why it has a very thick sediments at the edge of the continent. So imagine this length of the continent, this length of the continent has the same resources. Imagine that. how long the coastline is. And this is Nigeria. This has, yeah, I think that is Nigeria, if I'm not mistaken. So it has been deemed as one of the most desirable petroleum province in the areas in the world, perhaps. But then there are lots of pirates in there, so you need to kind of think again. But in South America, you would see lots of oils. And in here, closer to us, in Northwest Shelf Australia, they have lots of petroleum fields. We have Masela, right? The one will be going to be drilled, I don't know, in 2027 maybe. I'm not sure. But we have one areas that once was the passive margin of Australia. I think one of the lines I gave you in here, sorry, I think, hold on a second. I think this is one lines coming from the passive margin. You could see that. Look at that. That's a passive margin. You would see it has been deformed by the normal faults. You could see there, the normal faults, lots of normal faults, a very coherent normal fault, the edge of the continent. So it's gradually going into the oceanic crust, but then oceanic crust has already been subducted. What's left is basically these continental sections being dragged down and being thrust over in a Timor area. This is actually the seismic from the Northwest Shelf of Australia. You can see the sediments very, very, very thick. Yeah. So does that answer your questions, Tama?
Yes, thank you so much for your answer and your interested presentation.
Thank you.
Okay, Mas Alven, there is one question from Fermiro, and after that, maybe one last question from me.
Okay, so Faza Fermiro would like to know, is there any fracture aspect that is very important but currently isn't visible in seismic data? What is the latest research undergoing right now, and how much has it progressed in understanding fractures for others? Okay, one thing that I would like to raise in this talk is that, remember when I say about the scale, the observation scale, the depth, the last slide that I show you, this one from Fossen 2000 and sorry, it should be slightly bigger like that, so it won't go. So slides from Fossen, you can see that each and individual faults has their own damage zones. So you could treat it as one fault, but you could treat it as perhaps two faults combined together. So when you count the areas of the damage zones, you could see these areas being damaged. You can calculate the areas, the core, the fault core, the damage, the fault damage zones, and you can calculate the barrier between the area. Of course, it won't be feasible in the seismic scale, because one wiggle is how many meters now? One wiggle, about 30 meters still, Dr. Indra? One wiggle of seismic lines, I think that's 30 meters thick of sediments, roughly.
Okay.
So can you recall that? I think if I'm not mistaken, so one wiggle can be constitute to what 30 meters thick. So example, you have 7 seconds of sediments. Those 7 seconds of sediments, say you have 7 kilometers of rocks, for examples, yeah. And then you would see faults that simply very small, but then you can see that fault is basically displacing a one wiggle of seismic, displacing about a couple of milliseconds, right? Of course, you will not be able to see the width of the fault, because sometimes people interpret the faults basically only judging by looking at their only displacement. So you see the faults, they would map. So for example, this one, I can annotate this one. I think generally you would draw the faults going like that, and then that, doing interpretation like this. what we don't realize is that these thick lines that we drive there, it could have the informations of having an area as wide as this, for example. So the scale observations is really important. And then secondly, about the advance that has been carried out recently. As I also mentioned to you guys before in the talks, people now starting to realize the anatomy of the faults, the shape, the geometry can carries a great deal of what faults can influence into one particular areas. So people now looking at the relationship between faults length, faults width, faults movement, displacement, etc. So you can understand better about the faults. Some people even use length, displacements, and width to predict the magnitude of earthquake if it's happening at the moment. So you would expect, say, if I have faults like 10 kilometers long with displacement about 8 meters, I would create 5.6 magnitude of earthquake. People started to do that. In terms of explorations, as I mentioned to you before, is that some of the faults can be storage tanks, can be a storage for geothermals. So the resource is actually in the fault. Some faults can also only act as a permeability. The tanks is lower there, the tank is situated lower, but then the fault cross-cutting the tanks so that the faults acted as permeability. So now people is trying to pin down what is the actual roles of the faults. Is it a tank or is it simply a permeability? So to be able to know those things, it means that you would need to look very carefully on what actually the faults look like. Is it one large fault like here, for example, you would say this is one large fault, or simply maybe this is two faults different. Because then if you like to calculate the resources, say you only look at the depth at 500 meters and you know that this fault is a tank, for example, this is a reservoir for geothermal, you would only calculate these areas and then that area, and then you come up with a number of resources. But then people that looking at the deeper sections of the area said, no, look, the fault is connected. Why can't you count these areas being one resources? Certainly it can be very big. It changed the economy of the field, right? So those two things, be considerate about the scales that you are looking. Make sure that you are considering the scale, say that you are looking at the seismic data. Make sure that you're looking at the depth, how deep it is, how shallow it is, how narrow it is. When you do the interpretation, don't squeeze the seismic so that everything will be fault when you squeeze it, but try to do it in kind of more considerate scales, like 1-to-1 vertical and horizontal elevations, horizontal scale, so that you can see the actual geometry of the structures they looked at. And then secondly, when it comes to determining the faults being a tank or being a reservoir or being a permeability, it can hugely change the economy of the field, because you would come up with different ideas where you would think this is two faults being one, two separate faults being a reservoir, then to combine it into one. That's a big reservoir. So it can change a lot. Does that answer your questions, Faza? Faza's gone. Faza still there?
Yeah, I hope you answer his question. And maybe last question from me to close this class. It's not very related to the lecture actually, but I just curious. It's very interesting to see a geologist to fault identification. And I want to ask, in your opinion, is it possible to develop to develop a method to fault identification by using machine learning or something like that, or there is any study or research that develop that method, as far as you know?
Well, thank you. It's nice that you brought that up, and I also think I mentioned it on the lectures just now. People have been doing that for many years. Maybe for some of us who just learn about deep learning of the machine, we just heard it a couple in last couple of years, but I think people already done that since 10 years ago. Some slides that I showed you, I think particularly the last slides of my conclusions slide, the one on the left is basically made by machine.
Okay.
Quite interestingly. So basically the machine's program told the machine to make a line interpretation when you see a marker being cross-cut. So when you see marker being cross-cut, it immediately puts the line like that, like this, for example. You can see quite nicely there. I think, hold on, like so. Like in this one. So any sorry, I got confused by my own setup. Hold on a second. Okay. So any discontinuities, it will be put a line cutting across it. That's machine doing it. But what machine doesn't do is basically trying to make a connection between those faults. To see, you know that there will be a relay ramp of those faults. You know that the faults going to be one at depth, for example, this one, for example, here, this fault there, it's deep. It's actually going like that. So there is one major fault that's going slightly, oh sorry, it should be on this side there. And then there is smaller faults that are branching off from that one. So yes, machine can help you actually, but you still need to qualitatively adjust the topics, the efforts that has been going through by the machines. And yes, people have done it, and it is possible. But as automatic interpretation does, it carries a lot of uncertainties left, because then it will brutally place down the lines whenever it sees a displacement, whether is it important to geology or maybe less important, because then at the end of the day, you would need to see which fault that can be helpful to us and which faults aren't. So it's no use when you have mapped thousands of faults, but then those faults are not useful to us anyway. Or as you can see that some of them, the faults are quite definitive, very important in this area. They can explain the geology so that you can do it qualitatively. So I think a combination between us and the machine is the way forward. It can help us to speed up the process.
Okay, thank you very much for the explanation.
No worries.
It's an interesting discussion, but we have to end this class because the time duration, I think. I would to say thank you very much for you, Dr. Aven, to share your knowledge in this class so we can have a more understanding about the fault and the fracture clearly.
It's my pleasure.
Yeah.
Thank you for inviting me, Pak Wahyudi, Mas Indra.
Okay, Pak Wahyudi, do you have any comment for this class?
Okay, thank you. On behalf of our Department of Geophysical Engineering, we thank you very much for your valuable, interesting, attractive talk, Pak Alven. Yeah, it's a valuable value for us. Yeah.
Well, thank you very much, Wahyudi.
Okay.
Okay, and we hope
so
you can join us in the next IVC
Oh,
in October, I think.
In October.
In October, yeah. Yeah. Yeah.
Okay. Yeah, just let me know
Yeah.
if you would like to me bring out different topic, because to explain faults in 2 hours is, and to explain those styles in 2 hours where you have lots and lots of styles, you can individually address the faults. It's kind of challenging. And but I hope some of you may already learn about structural geology, and this is a revisit of your knowledge, and perhaps use it to a more elaborate sense to your benefit later.
Okay. Yeah. Okay. Thank you.
Okay. Maybe before we end this class, we can take a picture together. And please, Miss Harmita or Miss Rama, can you help us to take the picture?
Hebatan semua masih pada belajar ya jam 9 malam.
Friday night, tapi masih belajar.
Iya, beberapa udah familiar saya mukanya, soalnya ada di kelas saya beberapa nih. Iya kan, sebagian masih kelas saya kan ya, bagian nih.
We are maybe 14 foreign students here.
Ah, you got 14 foreigners. Wow.
Okay, everyone, we are going to the photo session. In my screen, there are 30 slides, so we will start from the first slide. 1, 2, 3. The next slide. 1, 2, 3. The last one. 1, 2, 3. Okay, thank you, everyone. Thank you, Dr. Alvin Rudiawan, for your presentation tonight.
My pleasure. I hope you are not getting a nightmare after you heard my voice for 2 hours non-stop.
Okay, thank you very much, Dr. Alvin. So maybe we can end the class, but for the students, please stay here for a moment because we have some announcement for you. Okay,
right, so,
Dr. Alvin, you might leave the room if you want.
Okay, thank you very much. I need to go back home because it's already 9. I'm still at the campus. It's really dark outside, and I'm alone, I think, at the building, so need to come out quickly. I'll see you guys soon.
Yeah,
take care.
See you soon. Have a good night.
Assalamualaikum.
Waalaikumsalam
warahmatullahi wabarakatuh.
Okay, so for the participants, we have some announcement. The first announcement is we have canceled the assignment at EduNext that ask you to submit the resume for every talk, for every lessons, and we, as a replacement, we make some quiz that you have done, and for the next session we also prepare some quiz, so it's the replacement as the previous assignment at EduNext. And then at the Sunday, at the Monday, we have some quiz, so prepare yourself with some lessons that have already done in this week's. Okay, I think that's all for the announcement from us, and have a nice day, have a nice weekend. Thank you. Bye-bye.
Bye. Thank you for all attendance, and see you again on Monday. So I end this session now for all.